as you all told, it will be done as a up counters or down counters, and also the another kind of counter is called up down counters. And after this one, you'll be using again modern type of counters also there. So these are the basic counters which we will be studying in our basics of electronics. First one is up counter, second one is down counter, and after that we'll be using up down counters. And the last one, it is modern type of counters. That was only up to the basics of electronics. Now let us see now the high level kind of counters, which are called as ring counters. Ring counters. Ring counter is a sequential logic counter that is constructed using the shift register. This ring counters have been constructed with the help of shift registers. I hope you all know the operation of the shift registers, which we have studied like in the previous of basics of electronics, like serial input, parallel output, and parallel input, parallel output, CFO, FIFO, and different kinds of serialing inputs and outputs. Parallel outputs have been obtained. Different kinds of shift counters we have studied there. Depending upon those kind of shift counters fundamentals, this ring counters have been designed. The same data recirculates in the counter depending upon the clock pulse. In the ring counter, what happens? The data will be recirculating depending upon what kind of pulse you are supplying over here. So now we can say that the ring counters basically are of two types. The first kind of a ring counter is called as an ordinary ring counter, and the other one, second one, will be called as an Johnson counter. So let us see one after the another in detail. For the first one, we are trying to take over here as a part of 4-bit ring counter. We are trying to study here. The ring counter is nothing else but it's a cascading of a number of flip-flops. N number of flip-flops have been used depending upon what kind of number or n bit counting you're trying to do. Depending upon that one, we'll be using the number of flip-flops. So now here, the ring counter is a cascaded connection of flip-flops in which output of the last flip-flop is connected to the input of the first flip-flop. This is how the recirculation takes place. Just now in the previous slide, I have told that depending upon the clock pulses, the data will be recirculated in the counter. So now I'm talking about the designing part. How does this ring counters have been designed? The ring counter is a cascading connection of flip-flops in which the output of the last flip-flop will become as an input to the first flip-flop. In ring counter, if the output of any stage is 1, then its remainder will be always equal to 0. So this is a basic of ring counter. Whenever the output of any stage, if any of the stage of the ring counter is producing an output as 1, then the remainder of this 1 is going to be 0. The ring counter transfers the same output throughout the circuit. This ring counter will be transferring the same output, whatever the output has obtained here, that will be circulated throughout the circuit. So this is a basic operation of a ring counter. That means that if output of first flip-flop is 1, then this is transferred to the next stage, that is to the second flip-flop. The same 1 is transferred to the second flip-flop. By transferring the output to its next stage, the output of the first flip-flop becomes 0. It means that now the particular output has been shifted from one slot of the counting element to the another counting element. So now whenever the output of the first flip-flop is 1, if that is being transferred to the second flip-flop, now the first flip-flop's output is going to become 0 because the 1 is shifted to the next level. And this process continues for all the stages of the ring counter. If we use a n number of flip-flops in a ring counter, the 1 is circulated for every n clock cycles. Means for every clock cycle, the shifting of this output will be taking place. Whenever the output first flip-flop produces some output, on the arriving of the clock pulse, that 1 will be shifted to the next flip-flop, and whenever it is shifted, the output of the second flip-flop will become 1, and the previous flip-flop's output is going to become 0. So this goes on continuing for n number of stages, for all the stages which have been connected. If you are talking about 4-bit ring counter, then it will be shifted. This process continues for the 4 stages of the ring counter. So see now, this is an ring counter diagram which has been designed with the help of D flip-flops. We are using here D flip-flops. You can see this is a flip-flop 1A. A is the first flip-flop, second flip-flop, third flip-flop, and fourth flip-flop, where you can see the last flip-flop's output is going to become as an input to the first flip-flop again. The last flip-flop's output is going to become as input to the first flip-flop, and the clock is connected over here. If a clock is connected simultaneously to all the flip-flops, we call it as what? Synchronous kind of counters. Okay, this is a kind of synchronous counter where the clock is connected simultaneously to all the flip-flops. But whereas in the asynchronous, what happens? In fact, in the asynchronous, this output has to become as a clock input. But since I have connected here all the clock as an input to the all the flip-flops simultaneously, I can call this kind of ring counter as an synchronous counters. And this is a reset button which is used to clear the data, and it will be used for resetting to all zeros. And here see now, here we design a ring counter by using the D flip-flops. This is called as a mod 4 ring counter, which has a four different D flip-flops have been used, which are connected in a series manner. The series connection of D flip-flops have been done. Since we are working with the 4-bit counter, we are using the 4 different kinds of D flip-flops. The clock signal is applied to the clock input of each flip-flop simultaneously. Therefore, we call it as a synchronous ring counter. And the reset pulse is applied to the clear input of all the flip-flops in order to reset that particular memory of the flip-flop. Now let us see the operation of this particular ring counter. The operation of ring counter is that here initially all the flip-flops in the ring counter are set to 0. With the help of reset, we will be clearing all the data. That data will be resetted to 0. Before applying the clock pulse, we apply the preset pulse to the flip-flops, which assign the value of 1 to the ring counter circuit. So before applying this clock pulse, what they do, they'll be applying a preset pulse. This preset is a kind of pulse which will make which will make this pulse, the flip-flop will be assigned to a value of 1 to the ring counter circuit. You can see it now. Initially, it will be made as 1. Okay. For each clock cycle, the data circulates among all the 4 stages of this particular ring counter. Whatever the data is there, once the data is obtained, what happens? That particular data on every clock cycle, that will be circulated. It goes from this stage to another stage, then this one will become 0 and this is going to become 1. And for the next clock cycle, what happens? If 1 is over here, assume the 1 has come over here from here to here. Now this 1 goes to the next stage and this 2 becomes 0, 0. So that's how the circulation takes place. This 4-staged ring counter is called as a mod 4 ring counter or else 4-bit ring counter. To circulate the data correctly in a ring counter, we must load the counter with the required values of zeros or ones, which we are supposed to circulate it. Before the circulating, we are supposed to make sure that the correct data has been loaded into this particular counter. So let us see now this operation in detail. We know that ring counter is similar to the shift registers, which is connected in the series. All these flip-flops are connected in series. So I can call it as a shift register, and the above diagram which is shown here is having a 4 kind of flip-flops. These have been done with the help of inputs like DA, DB, DC, and DD, which are nothing else but the inputs we can see here now. The 4 stages of flip-flops are connected parallel in serial. Our shift register, and with data inputs D0, D1, D2, and D3 are the data inputs. These are your data inputs which are connected over here. So now the data circulation in the ring counter is explained below. In this way, we can explain this one by passing the reset signal. Initially, the flip-flops are reset. Whenever the reset has been connected, you can see this diagram over here, reset diagram. By passing this reset signal, what happens? All the value flip-flops have been resetted. Whenever the preset has been applied to the ring counter, the input of the circuit becomes 1. The initial input is going to become 1 whenever the preset has been applied. So now this input is connected to the first flip-flop in series. The preset input, we have seen that whenever the preset is applied, what happens? The input has been resetted to 1. Before presetting, what we'll be doing? We'll be resetting all this particular flip-flop. So you'll be having only 0, 0, 0. All 4 zeros will be there. After resetting, you will be doing the preset. On the preset, what happens? The input will become as 1 over here. So that the same thing we have written. That one is applied to the first flip-flop in series, so that the flip-flop QA is set to 1. Now this flip-flop is having an output. That output is going to be set to be QA is going to be 1, and all other outputs of the remaining flip-flops will be low. The same thing. the first output of this one will become as 1, and all the other flip-flops output is going to become zeros. That will stay as very low. If we make a data input of the flip-flop A to low, whenever you give a data input over here, if the data input is triggered over here as low, why? Because the last flip-flop output is what? 0. If that becomes as an input to the first flip-flop, if you are giving a low input over here.
Sir.
Yeah.
Once explain again, sir.
Wait, which part?
Sir, you have said if we give input as 1 and all the other flip-flops will become 0. How, sir?
See, I was talking about the preset pulse. I was talking about the preset pulse. What happens here? Whenever you make it as a reset, whenever you apply a reset, on resetting, all the clear buttons will make the clock, the flip-flops will become a 0. Will be cleared. On the reset, the outputs will be 0, 0, 0, 0. Now, after the reset, what you'll be doing? We'll be applying a preset pulse. Preset pulse means what? What is this preset pulse? The preset pulse will apply the first flip-flops will be assigned to the value of 1. The first flip-flops output is going to be assigned as value as 1. On that stage, then only on applying the preset only will be starting your output. So see now, whenever you do the preset pulse, the first flip-flop output initially on the reset, what has happened? All the outputs were 0, 0, 0, 0. But whenever you do the preset pulse, the first flip-flops output is going to become as 1. And all the other 3 flip-flops will be 0 only. Okay, is it clear up to here now?
Have said that you have said that same output will be propagated.
Yeah, the same thing.
All the pulses, but the value is 0, na, sir. And we have applied a preset pulse as 1, so all the output should also be 1, na, sir.
See here, we have not yet started. We have not yet started the working of the counter. We have not yet started the working of the counter. It is before the application of clock. Whenever the clock works, then only the counter will be working. We have not entered still into the counting of this counting operation. This everything, what are the preset happens before the clock. That's what I explained here. Before applying the clock pulse, we need to apply the preset. What does this preset pulse will be doing? The preset pulse will be assigning the output of the first flip-flop as 1. That's the meaning of preset. It will not be assigning the output of all the flip-flops equal to 1. It will be assigning only the first flip-flops output is going to be 1. That's the operation of a preset. Once if it has been done, once the preset operation has been done, what happens? This is 0 and this is 0 and this is 0. So last flip-flops output is going to become as an input to the first flip-flop. It means what? You are triggering the first flip-flop at a low input. You are triggering the first flip-flop at a low input. So see now, this input, whenever the preset is applied to the ring counter, the input of the circuit becomes 1. That means this first flip-flop, this input is applied to the connected to the first flip-flop, which is connected in series, so that the flip-flop QA, the output of the first flip-flop is set to 1, and all the other outputs remaining will be low only. Low means what? All the outputs of the other remaining flip-flops will be 0 itself. This is not yet started. The counting has not yet started. The counting starts only on the application of clock. We have not started clocking pulse. We have not applied the clocking pulse. This happens before the application of the clocking pulse. Okay. So see now, if we make the data input of the clock flip-flop A is equal to low. Now we have applied, since the output of the last flip-flop is becoming as an input to the first flip-flop. The output of last flip-flop is what? After presetting, it is 0. The same 0 is given as an input to the first flip-flop. Whenever it is given as an input to the first flip-flop, means you are inputting the first flip-flop with a low input. If you make the data input of the flip-flop A to low, this gives us a data pulse as 0, 1, 0. Now what is happening? Whenever you are giving this data low, what happens? Whenever you give this one, then the pulse becomes as what? 0, 1, 0. Then for the second clock, what happens? The first flip-flop will again change, and the output of the B will become as high. So see now, in this case, what I have told, it is now 1. It is now 1. Listen here, ma. Don't make any kind of disturbance over here with your mic. So see now, whenever you applied 0 over here on the first clock, the shifting takes place. Now the shifting takes place. Whenever the clock is applied over here, this 0 becomes as an output over here. So now this is 0 means the 1 goes to the next flip-flop. The 1 becomes as an input to the next flip-flop, and this goes to the next one. Therefore, we have written here, whenever we make a data input of first flip-flop to low, this gives an data pulse of 0, 1, 0. For the 3 flip-flop, what happens here now? The data pulse will be 0. This 1 goes to the next phase, 0, 1, 0 for the first cycle, and this will be anyway 0 only. So next one, for the second clock signal. For the second clock signal, what happens? The output of the first flip-flop will again change. The output of the first flip-flop will change, then the output of the second flip-flop will become as high. For the second clock cycle, what happens? This becomes a high, so this is going to change again. So the one is going to shift from one flip-flop to another flip-flop. It goes on shifting. So ultimately, this will become as 0, 0, 1. In the previous case, what has happened? Whenever we have applied the first clock, this output has become 0, and this 1 has shifted to the second stage. So your output will be what? 0, 1, 0, 0. Whenever the second clock comes, clock comes means, just a minute, I'll try to note it over here. For the first clock, 0 has been applied over here. Why 0 is applied? The output of this one is becoming input to this one. The same 0 comes over here. So if the first clock, the output will be 0, this will be 1, and this is going to be 0. And anyway, it will be the same thing. Now, when this is happens at the first clock, let us assume now for the second clock has been applied. If second clock is applied, what happens? This is going to shift over here. If it shifts over here, this becomes output becomes 0, and this is going to be, this 1 is going to shift it to the next stage. So your new output will be what? On the second clock, 0, 0, and 1. So that becomes your output. So see, the same thing we have written. On the second clock, whenever the output of this one will become 1. So now whenever we apply the second clock, where is that one? Yeah, here. Whenever we apply the second clock, the output of this one, the data pulse, is going to become 0, 0, 1. The same thing we have obtained here. The shifting takes place from this second stage. Excuse me, I'm not finding. Yeah, pointer. Yeah. See now. From now the output has changed. For the first clock, it has become 0, 1, 0. For the second clock, what happens? Again, it has to change. The 0 comes over here and the 1 has to go over here. So it becomes 0, 0, 1. So this is the operation, how it happens with this particular ring counter. You can see now the same thing in the truth table, we have kept it here. In this way, the clock signal and the input of the first flip-flop changes, and the output of the other flip-flop also changes. As the output of the last flip-flop is connected in series with the input of the first flip-flop, the data sequence goes on rotating all the time. The data sequence will be same. It was earlier, it was 0, 1, 0, and second, for the second clock, what it has happened? 0, 0, 1. The same thing happens. So let us see the truth table of this ring counter. What happens in the ring counter here? Whenever the clear input is clear equal to 0, whenever the clear input is equal to 0, all the flip-flops are set to 1, and whenever the clear input equal to 1. So this is the design part. Whenever the clear input is equal to 1, the ring counter starts its operation. So now whenever the clear is being made as 1, then the ring counter will be starting its operation. Means I'm talking about this particular part. See now, clear inputs, where it means the clears are connected to the reset. So whenever the clear equal to 1, means if the reset is going to become 1, whenever you are applying a high pulse over here, all the clears are going to become 1. Then only the clocking network, this particular counter will be starting, or else it will not be starting. Whenever the reset equal to 0 at low state, if it is 0 means what? It will, all the flip-flops are set to 1. So now whenever the clear equal to 1, then only the operation starts. So let us see how the operation just now, which we have studied. For the first clock signal, the counter starts its operation. On the next clock signal, the counter will be resetted to 0, 0, and the ring counter has got the 4 sequences. The first one is what? You have got this outputs over here. Q0 initially what we are having? 1, 0, 0, 0. Q0, this is a Q0 output, Q1, Q2, Q3. So see now. Q0 first initially 1, 0, 0, 0. For the next clock cycle, this 1 will be shifted to this one. The 1 will goes on shifting to the next output. So it goes shifted to this particular stage. When it shifts, what happens? this will be connected to this last final output will become as an input to the first flip flop. So therefore, you will get the output over here as 0. Then this is coming over here. The output of first one will become as output of the second flip flop, and the other two will be 0 0 only. And again, in the next stage, what happens if for the second clock pulse, again this will become as an input. This third last output will become as input, and this one comes over here. So this counting goes on in this way. So ultimately, at the last sequence of the clock, you'll be having an output of 0 0 0 1. So this is what happens with the counting process of the ring counter. So this is how the ring counter will be working depending upon the 4 different clock pulses. You can see the same thing. We have put it in terms of a diagrammatic part also. The timing diagram of the ring counter will explain that clock signal changes the output of every stage of the counter, so that the clock signal will help to circulate from one flip-flop to another flip-flop. The output is going to circulate from one flip-flop to another flip-flop. As a 4-bit ring counter has got the 4 stages, or else it is having the 4 flip-flops. This circulation will be starting with the preset button or the preset digit with the 1 clock signal, and the output frequency of the flip-flops will be always 1/4 of the remaining clock cycles. So CMM. This is a clock which you have given over here. Whenever you give this one, the shift changes for the first stage. Shift will be changing, and the outputs will be coming depending upon this one. As I told you that your preset clear has to be equal to 1. Whenever the clear becomes 1, then on the clocking or the counting will be working. Whenever the clear equal to 1, then it starts working. Initially, it was 1 0 0. On the preset, what has happened? The first output is 0, and the second, all the 3 outputs will be, sorry, the first output is 1, and all the 3 outputs are 0. Whenever the clear is going to become 1, then the working condition of the ring counter starts, and ultimately the 1 comes over here. If 1 comes over here, and for the next clocking stage, what happens? This 1 goes over here. So in this way, simultaneously, for the final stage of the output, you'll be having an output of 0 0 0 1. So this is the timing diagram or the waveform of a particular truth table which you have seen in the previous slide. So what are the advantages here? This can be implemented by using D flip-flop and also JK flip-flop. It has got a self-decoding circuit where it can decode depending upon these 3 signals: clock, preset, and also reset signals. It can decode. And again, the disadvantage is that it is having, since we are using the 4 cycles, it will be having the 15 stages: 0 0 0 stage to 1 1 1 stage, all one stage. So it is having the only 4 of 15 stages have been utilized over here. So this is regarding what is meant by ring count.